Okay. So which of the following structures represents the most stable conformation? Okay, it represents the most stable conformation of the molecule shown below. So I'm going to draw the structure in chair form, okay? And then I want you to think about it while I'm doing it. All right, so let's see what we have done here. So we have a molecule where the two methyl groups in the 1,4 position, they are cis to each other. They're cis to each other, okay? And this methyl and the isopropyl, they are trans to each other. So when they give you the structure in two-dimensional, okay, skeletal structure, it is always good to draw your own chair form, okay? Don't take shortcuts there. It will save you a lot of time. So when the two methyl groups are cis to each other in 1, 2, 3, 4, 1,4 position, right? One of them have to be, if you have one of them in axial position, the other one has to be in equatorial position, right? So this is the axial hydrogen, and that is the equatorial hydrogen. And the easiest way I teach is connect the two carbons with a straight line, all right? And if the CH3s are on the same side, then that is cis. Okay, so this methyl here and that methyl, they are cis because they are both broken wedge, right? They are cis to each other. And this methyl and on the second carbon, the isopropyl, they are wedge and broken wedge. Therefore, they are trans to each other. So if this is axial, then this one has to be axial as well, right? That one has to be axial as well. So how do you know? Again, like, draw a line, which is essentially this bond here. Draw a straight line between the two carbons or connecting the two carbons, right? And you can see, okay, that the CH3 here and the CH and the isopropyl here, they are on the opposite sides, right? So I mean, if you stand here and look at it, this hydrogen will be above the plane. Okay, so obviously this is below the carbon, below the straight bond, and this hydrogen will appear above. So they are trans to each other. Now for this molecule, the isopropyl group is is axial, which is not very stable. So if you want to draw a stable conformation, you have to make sure that the isopropyl is equatorial, right? And this goes axial, sorry, CH3, right? And this goes, this goes equatorial, right? And that goes to axial, okay, CH3, right? So here, the answer that has CH3, one axial, one equatorial, and the isopropyl equatorial is going to be the right answer, okay? This fourth carbon axial and these two in equatorial is going to be the right answer. And in this conformation, you can also see that the methyl groups, only one methyl group is in axial, and the bulky isopropyl and the bulky methyl group, two of them are going to be in equatorial position, which is stable because they will not have the 1,3 interaction. All right. So any questions about this? Okay. So let me get the chat up. Okay. All right. So let's go to the next question. Okay, so here I want you guys to think about it a little bit, okay, and see if you can give me an answer. So you have, I'm talking about it, but you can think about the answer and type the answer if possible. So you have an alkene bond here, group here, and you have an alcohol group here. This is chromic acid, which is a strong oxidizing agent, okay, which is very similar, which is parallel to your Jones reagent. Jones reagent is when you have your sodium dichromate with sulfuric acid, which generates chromic acid. That's what you have here. And it's going to oxidize the molecule. But where exactly it is going to oxidize, we should know, okay? So what do you guys think? A, B, C, and D, okay? Which is the right answer? D, okay? Yes, that is the right answer. So essentially what you need to know is you will convert your alcohol first to an aldehyde, okay? First to an aldehyde. But since you have chromic acid in the medium, it is not going to stop at the aldehyde stage. It is going to convert your aldehyde further into a carboxylic acid, okay? And that's essentially what your answer is. And your chromic acid or Jones reagent or those strong oxidizing agents will not go after your double bond. So that is going to stay intact. So that is the right answer. Okay. And A is not the right answer because you will not stop at the aldehyde stage. Even though aldehyde is an intermediate, it is going to further oxidize that into a carboxylic acid. That is a ketone, right? That CH3 comes from nowhere, and this is a diol. So don't do those mistakes of miscounting your carbons. Okay, let's go to the next question. What is the order of increasing acidity of the set of compounds seen below? So what is the right answer here? Okay, so the strongest acid here is a carboxylic acid because you have, so whenever you have an acid and you want to see which of these acids is a strong acid, always write the conjugate base, right? So always write the conjugate base and see which one is more stable. The more stable the conjugate base, stronger the acid you start from. So that is the conjugate base for the phenol there, and then you have the conjugate base for the alcohol. So this one, the electrons are only held by the atom. It is not conjugated. Here the electron is conjugated into the phenyl ring, and here the electron is conjugated into the oxygen atom here. So this is conjugated, this is also conjugated, but since this electron is conjugated with the more electronegative atom, that is going to be the most stable base, second most stable base, and the least stable base. So it's going to be 3, 1, 2, or so increasing order. So it's going to be 2, 1, 3. That is the right answer. That is the right answer. Okay. Any questions? All right. Okay. Let's do a synthesis problem. From the compounds below, choose the major product that will result from the following reaction. The major product. So here what happens is sodium borohydride is a reducing agent which can reduce ketones and aldehydes, okay, but it is not capable of reducing esters or carboxylic acids or amides, okay, esters or carboxylic acids or amides, okay. And the reason why sodium borohydride cannot reduce these acid derivatives is because, again, the lone pair, right? Because the conjugate that makes this carbon less electron deficient. And since sodium borohydride is sort of a weak reducing agent, right? Lithium aluminum hydride can do that, right? When you have sodium borohydride, because you have boron, okay, when you have aluminum hydrogen bond, aluminum is a lot more electron rich, so it will make the hydride more electron rich, right? The sodium borohydride has a BH bond, which is not strong enough to reduce these. So you will only reduce the carbonyl here. You will not reduce the ester here because that carbon is not as electron deficient as this carbonyl is. So remember, these concepts should be remembered in unison. In carbon 13, there is a difference between a pure carbonyl and a conjugated carbonyl. In IR, you see a difference between a pure carbonyl and a conjugated carbonyl, as we saw in the spectroscopy problems today. And same thing happens because sodium borohydride is a weak reagent. It will not reduce the carbon here that is part of the conjugated carbonyl, whereas it will reduce this carbon. Therefore, the right answer for this question is let's see, A, B, C, and D. So A is the right answer. Okay, because it reduces that. It will not be able to touch the double bond here, or it will not be able to touch the carbon oxygen double bond here. Okay, any questions? Okay, so now what I want to say is, just since we are here, okay, we can talk about this. If this was lithium aluminum hydride, okay, if this was lithium aluminum hydride, then you will definitely see more action than what you see here. It will be able to reduce the carbonyl to an alcohol. It will also be able to reduce your carboxyl acid to ester to a alcohol as well, okay. And you'll also be able to see some 1,4 addition chemistry. I don't want to get into the details of it. It will get too complicated, and I don't want to waste time. But yeah, so you will see a lot more action when you take lithium aluminum hydride, because it is a stronger reducing agent. That is because the aluminum hydride bond is a lot more electron rich due to aluminum being a larger atom with a lower electronegativity. Remember, boron is right above aluminum, and it can make the same tetrahedral structure like boron does, and the reactivity is very similar, except this is a much stronger reducing agent. Okay. So organic chemistry is always easy to remember these concepts in clusters. We can remember these things together. Okay, like I mentioned, the carbonyl thing and lithium aluminum hydride and sodium borohydride. Okay. All right. So let's see if somebody can answer this question. Which of the following reaction is most likely to occur? Anyone has an answer? Okay, I see C. Yes, that is the right answer. Okay, so let's see why the other reactions won't work. C is essentially what we just discussed right now. So I'm not going to discuss this in detail. Okay, so here, right, the chloride can donate electrons, but the hydroxide is a poor leaving group. So chloride is a decent nucleophile. Okay, in some cases it is a good nucleophile as well. So decent to good nucleophile, but hydroxide is a poor leaving group. Therefore, this reaction won't happen, because when the hydroxide leaves, right, it is not going to be very stable. So it's not a good leaving group. H2O is a good leaving group. If you protonate that into a H3O plus, that is a good leaving group. Okay, that's the reason, since alcohols or the hydroxy group does not leave voluntarily, you'll convert that into a good leaving group by converting this into a tosylate. Okay, if you take this alcohol and convert this into a tosylate, which is what? That S11O, right? Para-toluene sulfonyl chloride. That alcohol will become a tosylate. If you have pyridine, the pyridine will abstract the proton. So that becomes a good leaving group. Then the reaction works really well. Because hydroxide is a poor leaving group, you are constrained to make this into a tosylate to make this reaction work. Okay. Let us look at this. Bromine won't work. Bromine by itself is not going to be a good electrophile unless you add FeBr3. Then this reaction will work. And even then, you're not going to reduce that, okay, unless you have a source of hydrogen or something. So this reaction is absurd. It doesn't make sense. When you have NBS and light, you release Br dot. Okay, from NBS, N-bromosuccinimide, remember, is a structure that looks like that. It's a nitrogen, bromine, N-bromosuccinimide, okay? And that, in the presence of light, is going to give you bromine radical and the succinimide radical, okay? And that's the reason this whole thing works, as a matter of fact. And so, but the thing is, the bromine radical is going to give you, okay, allylic substitution. It's going to give a substitution in those positions. Therefore, substitution on that carbon is not what we are looking for, not what happens. Okay, therefore that reaction won't work either. So these three won't work. This is the right answer. Okay. What is the major product of the following reaction? So here I won't waste time asking you to answer. So let's look at this right away. Sodium borohydride, what is going to happen is, as I told you, your amide is not going to be touched by sodium borohydride, because the lone pair will make this carbon less electrophilic. So sodium borohydride will only reduce the aldehyde to an alcohol. So we are looking at, okay, give me a second. So, okay, so we have an alcohol, right? So 2, 3, 4, 5, 6. Okay, you have double bond O and then a nitrogen and that. Okay, all right. So label this. Okay, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. If you like me, if you stumble, just right away label the carbons. And then you are treating this with acid, which you are simply converting the O minus that comes from sodium borohydride reaction back into an OH. All right, that's what is going on here. You still have two hydrogens. That one hydrogen is there, the other one is there. Now what you're doing is treating this with sodium hydride. Sodium hydride is a very strong base, which will deprotonate this alcohol. All right, so it will not do anything again to the amide part of the molecule. It will only convert the oxygen to, or the alcohol to an oxide. And now if you treat this with benzyl bromide, okay, benzyl bromide, what happens is you will have a substitution reaction, especially because it is a primary carbon. If this was a secondary or a tertiary carbon, you might see an elimination, okay, reaction, therefore, or eat by U2 mechanism. But this is a primary carbon, you'll only see elimination. So you're essentially going to substitute and make an ether, all right? So the NN dimethyl part is going to be kept, and you will have your, you'll have your that, okay? So let's see, that is going to be not this, not this, not this, because you convert that into alcohol, and that is the right answer, okay? All right. Okay. All right, so let's see if somebody can answer this question. You have, okay, before you answer the question, I want to ask you, what is this functional group called? When you have a carbon, right, and two ethers from that carbon, which is what you call a geminal dihydroxy, okay, or diether, geminal diether. What is that functional group called? Does anybody know? It's called an acetal, exactly. All right, it's called an acetal. An acetal is a carbon, right, which has, say, R, you have an OR and an OR, okay? OR, that's an acetal. And if you have a cyclic structure, it is more stable because of entropic reasons, okay? Hopefully you have been thought about this. And if you have something that looks like that, okay, an OH and an OR, that is what you call an hemiacetal, right? And a cyclic acetal, because it's thermodynamically more favorable, it is used as a protection group chemistry because it can lead to the corresponding carbonyl. I will talk about that. So what is the right answer for this question? The right answer is, let's see, you have Wolff-Kishner reduction. That's what this is, okay? Wolff-Kishner reduction. And when you treat it with an acid, you will be able to convert your carbonyl to a CH2, okay? So all those are CH2. So just by looking at that part of the molecule, you won't be able to tell what the right answer is, okay? So this part is protected, is essentially what I'm trying to say. This part is protected. If you use hydrazine with potassium hydroxide, it will reduce your carbonyl to a CH2, okay? So now tell me what the right answer is. Now that I have given you that part, what is the right answer? The right answer is A. The right answer is A. Why? Because what happens is when you add hydrazine, you will end up forming the imine first, all right? You have that. You'll form the imine, okay? Potassium hydroxide acts as a base. It helps you form the imine. The other side is still unreactive because the acetal is not reactive to any sort of nucleophile like that. And now when you treat this with acid, okay, and you heat this, what happens is this whole thing becomes a nitrogen, right? So there is a mechanism aspect to that. I don't want to go into the detail of that, but it's a very interesting mechanism. So this whole molecule, the hydrogens will rearrange to go on this carbon, and you will end up making a CH2. So if say, for example, this was ND2, right? You'll get two deuteriums on that because it rearranges, and this becomes nitrogen. You remove nitrogen from this molecule. And when you treat it with water also, simultaneously, what happens at the same time is you'll convert your acetal into a ketone, right? Acetal into a ketone. So that's basically what happens, especially when you treat it with acid and you heat it, you remove water out of this molecule. So anytime you have a ketone, right? Anytime you have a ketone and you add water to that, right? Water can act as a nucleophile and you end up forming an OH, an OH2 plus, all right? And if this is an alcohol, you form acetal. And if this is ethylene glycol, then you form an acetal that is cyclic, which forms fairly easily. And if you can remove the water using like Dean-Stark apparatus or something, the water will put, so this is always going to be in equilibrium. And if you're able to remove the water, you can push the equilibrium towards the right, okay? And you can remove the water by using, by heating and evaporating the water. So that's kind of a background. So the right answer is this, because you reduce the ketone to a Wolff-Fleischner, and you're converting your acetal to a ketone. Okay. All right. So that's that. Okay. What is wrong with the following reaction scheme? This is one of the very often tested Grignard concept. So let me see if you guys can think about it and tell me what's going to happen. What is the right answer? Anyone? Okay. So Grignards, what do we know about Grignard? So Grignards, so if you look at this is propyl magnesium bromide. That is carbon. And even though we write it like that, MgBr, most of the reactivity of Grignards is very easily understood if you look at it like a carbanion with a metal center, with a metal so as a metal salt, right? Br minus. Magnesium is always 2+, we know that. So magnesium bromide, these two are not usually going to participate. So you have a carbanion. So now you have a carbanion and you're adding a molecule like this, right? A molecule like this. What do you think will happen? So usually when you see a carbonyl, you will think that you are going to have a nucleophilic attack on the carbonyl center. That's what you think, right? But that is when you do not have the amino group or a hydroxy group or a carboxylic acid, any of those things which has a protic functional group. Okay, we know protic solvents, right? Ammonia is a protic solvent because the hydrogen is attached to an electronegative atom, which is nitrogen. Okay, water is a protic solvent, obviously, right? Methanol is a protic solvent. All these are protic because the nitrogen or oxygen, they pull electrons away from the hydrogen, making it significantly partially positively charged. So when you have a carbanion, even before the carbanion can react with, for a nucleophilic reaction, you're going to have an acid-base chemistry. So this proton is going to neutralize the carbanion, leaving you with an alkane. All right. So that is why when let's say this is an OH, right? You guys would have seen this. If this was an OH, if this was an alcohol, right? Same thing happens, which is why if you have a molecule which has an aldehyde and an alcohol group, you should first protect this before you have a Grignard reactivity. And after the Grignard reactivity happens and you make an alcohol, you will deprotect it, right? So the right answer to this question is the Grignard reagent will deprotonate the amine group, yes, instead of attacking the carbonyl group. So that is the right answer. Okay, that is the right answer. So since we talked about protection, right? How do you protect an alcohol? How do you protect an alcohol before you react it for Grignard? Anyone? You will use TMSCl, trimethylsilyl chloride. Remember that? Okay. If you use silicon 3-methyl, right, and a chlorine, that alcohol, right, will do that. Okay. Acetal formation. Oh no, so that's a previous answer. Okay, yeah. So you'll do that and you will make an oxygen, TMS, right? And then you have your aldehyde here. Now you treat this with sodium borohydride or whatever you want to reduce. Sorry, Grignard, even sodium borohydride, whatever you want to do. And then it'll react. And once the reaction happens, you get the alcohol. You'll treat this with acid and water or TBAF. That'll be protected. Okay. All right. So if you remember that, well and good. If you didn't remember, just watch this video later and understand what's going on. Okay, let's see if somebody can answer this question. What are the missing reagents? You're going from an alcohol, the cyclic structure is still there. You're going from an alcohol and you're converting that into an amide. Okay. So what is the right answer to this? Anyone? Okay. All right, okay. So we have C as D as like a couple of answers, okay. All right, so let's see. Since I got D, I'm going to look at D, okay. So KMnO4, what does KMnO4 do? It'll convert the primary alcohol to an aldehyde, and then it will continue to a carboxylic acid. So KMnO4 and Jones reagent, which is a chromic acid, should be remembered in unison again. Always remember things in pairs. They're almost the same, not big difference. So this will convert the cyclic structure into a carboxylic acid, okay. SOCl2. What is thionyl chloride? It is a good chlorinating agent. Thionyl chloride is, know the structure. That is also good practice in organic chemistry. Just don't remember reagents as just like formulae. Know the structure. So it is very good at converting an alcohol to an alkyl halide, okay, or Cl. It is also really good at converting carboxylic acids to the acid chloride. This one will keep the C11O and then Cl. So it will convert to an alkyl halide, convert to an acid chloride as well. So now what happens with thionyl chloride is you will get the corresponding acid chloride. Now, acid chlorides are really useful synthetic intermediates. They are one of the most useful acid derivatives. Okay, if this is an acid, carboxylic acid, acid chlorides, esters, amides, these are all called as acid derivatives, right? This is very useful because you can take a nucleophile, okay, and the nucleophile can add like that. I'm writing a mechanism right now, so don't get confused, okay? So you can get O minus, and then you can have the chlorine here and the nucleophile. So nucleophile adds, and then the nucleophile will eliminate because chlorine is a good leaving group. So you have an addition elimination mechanism in play. And what will happen is you'll get a double bond O with the nucleophile. So in this case, the nucleophile is the amine. So this is the mechanism. And if you use the nucleophile, use an amine in place of the nucleophile, which is NH3CH2, you will end up getting the product, right? NH2CH3. And one more side note, you will generate a lot of H plus in this reaction because one of the hydrogens from the amine is going to be kicked out as H plus. If you add excess amine, okay, the other amine that is floating around in the medium will pick up this proton and it will act as a base as well. So you do not have to add pyridine, just the excess amine. So you will usually add two equivalents of amine, and one equivalent will act as the nucleophile, the other equivalent will act as the base to scavenge off the proton. All right, so the answer to this question is option D. Okay. All right, so that is that. Now let us look at question 50 here. So of the following compounds, this also people should be able to answer. And thanks, we have right answer so far. Of the following compounds, which will not be deprotonated by sodium methoxide? Which will not be deprotonated by sodium methoxide? What do you guys think? The answer is B. All right. Why? Carboxylic acid, if you take a conjugate base of this, right? Then this is more stable than this. That means methoxide is a stronger base and this is a weaker base. That means this will deprotonate the acid and not the other way around. Okay. So that's one way to look at it. So if you look at all these species, right, these two hydrogens are going to be very acidic as well because you have two carbonyls, right? So this is what you call an active methylene group, by the way. Remember that, okay? So the carbanion that you generate from kicking out a proton, it is very stable because it has two carbonyls that can stabilize this by resonance. This also is stabilized by resonance. So here the oxygen is held by, the electron is held by just the oxygen, whereas here the electron is held by the oxygen plus the electron is also delocalized, making this stable. Therefore, this is a weaker base, that is a stronger base. Therefore, the stronger base can deprotonate the acid to make the corresponding phenoxide. So this is the only one that is not going to be deprotonated by sodium methoxide, because if you look at the conjugate base structure, the anion you generate is a much stronger base, which means if you make alcohol from methoxide after deprotonating the ether, the carbanion is going to make sure that it pulls the proton back and push the reaction back, making this the major product. Okay. So for acid-base chemistry, always look at both the conjugate base and the acid. So the more stable the conjugate base is, the stronger the acid. Okay. So what is the major product of this reaction that you see here? So I'm going to solve it right away without waiting for it to answer. So 3-pentanone, you should know how to name these ketones and aldehydes. If it's an aldehyde, it's going to end with an al. Okay, not all. It's going to end with an al. Okay, usually an al. Okay, so 3-pentanone. 3. Okay, it's a ketone. You're treating this with ethylamine. Okay, you're treating this with ethylamine. And you're treating this with an acid, catalyst. A small amount of acid is added. So I just want some answers, like, when you treat a ketone or an aldehyde, okay, or an aldehyde with amine, with catalytic amount of acid, what is the name of the functional group of the molecule you get? What is the name of the functional group of the molecule you get? So it is what we call an imine, right? Imine. This is an amine, right? Imine means you have a nitrogen with a double bond, okay? So what's going on is your nitrogen is going to act as a, I'm going to give you a brief mechanism, but like, hopefully you can follow this, right? That happens. And you will, because nitrogen is a good nucleophile, remember that, okay? So, and this is an electrophilic carbon center because carbon loses electron to the oxygen due to electronegativity and resonance, okay? So you will end up having O minus, okay? And you will have, the R group, right, which is the ethyl group. And the H plus in the medium is going to protonate, okay? That, okay? You get OH and you get NR, H2, okay? H2 with a positive charge. And now what happens is you protonate this again with the acidic, acid in the medium, and you'll convert that into a good leaving group. And what happens is, you'll pick out the proton. I'm not giving you a full mechanism because for obvious reasons. So you will end up making a nitrogen with a double bond. Okay, you'll end up making a nitrogen with a double bond, and then the ethyl group. You will lose both the protons. Okay, in a sequence, and you'll form an imine. So that's essentially is what's going on. So that makes this the right answer. Okay, that makes this the right answer. All right. Okay, so that is that, and the same reaction applies to aldehydes as well. All right, so let's look at this. The tolerance test can be used to distinguish between which pairs of compounds. So what is tolerance reagent? Tolerance test means you have the tolerance reagent, okay? So what is tolerance reagent? Do we know? So tolerance reagent is when you have an aldehyde, all right? So let me give actual next structure. It's easier to remember that way. So let's say you have propanal, okay? And you add Ag2O, silver oxide, okay, and in ammonia, right? This is what you call ammoniacal silver nitrate, right? It is added in the form of silver nitrate, but Ag2O forms that's the active species and all that. But ammoniacal silver nitrate is what it's called. So when you have ammonia and silver and or a silver nitrate, Ag3, right? Silver is 1 plus in this. What happens is you will oxidize your aldehyde to a carboxylic acid. Okay, so that's what the oxygen role here is. Okay, you'll oxidize that into a carboxylic acid, and more importantly, what happens is you'll convert this into silver 0. Okay, silver 0. Silver goes from silver plus 1 to silver 0. So why is this reaction special? Is after the reaction is over, you do this reaction in a test tube, let's say, for example, right? The silver metal actually forms a nice coating because we know how silver metal looks, right? It forms a nice coating, and the whole surface of the test tube, especially when you look at it from the outside, looks like a mirror. That's why it is called as a silver mirror, because of the metal coating, right? And so another reason why it is very useful, other than the visual appeal, is when you have an aldehyde and you don't have spectroscopy to look at it, right? If you see a silver mirror, which is a positive visual test, if you do any other reaction, you won't be able to see visual change. But a silver mirror can show you visual change that confirms the presence of aldehyde in a molecule. Okay, that's one usefulness of silver. mirror test. And the other usefulness is, like, say, for example, you have a molecule that looks like this, okay? That has an aldehyde group. Sorry. That has an aldehyde group, okay? And that also has an alcohol group, let's say, okay? And you want to oxidize your aldehyde exclusively to a carboxylic acid without touching the hydroxy group, okay? You can use the tolerance mirror test or tolerance, like, ammoniacal silver nitrate, because ammoniacal silver nitrate is very specific. It will only oxidize the aldehyde to a carboxylic acid. It will not touch your alcohol. Whereas if you do something like Jones reagent, PCC, all those stuff, even PCC, right? PCC is selective, okay? A PCC won't oxidize your aldehyde to a carboxylic acid, but it will oxidize your alcohol to a ketone. Or if you use Jones reagent, K1O4, all those things will convert your alcohol to a ketone, and then it will also convert your aldehyde to a carboxylic acid. So tolerance mirror is a very useful qualitative test, and it is also very useful as a synthetic selective oxidation reagent. Okay, so that being said, right, I kind of went into a tangent here because to give you background. So what is the right answer here? Okay, what is the right answer? It can be used to distinguish between something that has an aldehyde and something that does not have an aldehyde, all right? So for example, this has a ketone, that's a ketone. This has an aldehyde and a ketone, and this has an aldehyde. So tolerance mirror will not react with this, it will not react with this. Therefore, it cannot distinguish between these two ketones. Tolerance mirror will react with this, it will also react with this. Therefore, here also, it cannot distinguish between these two molecules, okay? In C, tolerance reagent will oxidize this and show a positive mirror, and it will not oxidize this and will not show a positive mirror. Therefore, this is the situation where you can use tolerance reagent to distinguish between these two molecules. And here also, tolerance reagent will not react with either. Therefore, you cannot see that, okay? See the difference between the two molecules. Okay, so any questions so far? Is the pace okay, or do you guys want me to slow down or go faster? Okay, all right, thank you. Okay, 10 more minutes before we take the next break, okay? So let's look at, so after this, I will start solving some statement problems because not all of MCAT problems are going to be pure organic chemistry, but knowing these basics will actually be useful even in statement problems, but I will start looking at some statement problems after this, okay? So what is the predicted product in the following reaction? Now, one thing I want somebody to answer is, what is the name of this reaction? What is the name of this reaction? So you have an aldehyde, okay? And you have a phosphonium salt, all right? And this is what you call the yelide, not yield, okay, by the way, but so E-L-I-D-E, Y-L-I-D-E, not, all right? This is what you call an yelide. And this is so this gives you an alkene, all right? So that carbon here, even though, like, no, they put a negative charge on the end here, your phosphorus has 3 phenyl groups. It has 2 hydrogens here, the carbon, right? And even though this bond is, like, no, is considered to be a single bond. Sorry, you have, this is actually a negative charge, right? By the way, keep them, even though we have a bond here, right? This carbon has a lot of negative charge to it. That's essentially what I'm trying to say, all right? And the phosphorus here has a positive charge. So even though we see a formal bond, it is pretty much like Grignard. There's a lot of carbon with a negative charge here, okay? And this is what a phosphonium salt is. Because it has a phosphorus with a positive charge, all right? So when you have a carbonyl with a C double bond O, right? This carbon here is going to attack the carbon center, okay? And you get oxygen with a negative charge, and then the phosphorus will make a bond with the oxygen and it will leave, and you end up making triphenyl phosphine oxide, okay, phosphine oxide. And what happens to the carbon? It's essentially going to make an alkene. So that is basically what this reaction is, all right? Okay, so you have a carbon with a double bond, and you have that carbon is this carbon, and then you're going to have a CH3, and that carbon has 1 hydrogen to it. That's what I was confused about. Why I have extra bonds, right? Okay, sorry about that. Okay, so that's essentially what. Okay, so that one hydrogen is still the same hydrogen that is with this carbon. And okay, that carbon is the carbon here. And you usually get a trans molecule. But one thing about this reaction, which is what you call a Wittig reaction, right, is that it is very hard to predict stereoselectivity. We cannot always say you're going to get trans. We cannot always say you're going to get cis, okay? But generally trans is formed, that's what. So based on that, the answer to this question is going to be what, let's say OH. So OCH3, all right? So that is going to be the right molecule. Here we have an OH, right? So that's not the right structure. And this is a Wittig reaction where you have an alkene, all right? And as I said, it's not possible to predict whether you get cis or trans, but yeah. So your answer can have both cis and trans, and both are equally valid. Okay, all right. Okay, so let's see if somebody can answer this question. So what is the order of intermediates? They're asking you the structure of these parts in the multi-step synthesis, right? So you have acid, and what is this functional group in the molecule here? It is a ester, okay? So this is, so anytime you have to remember this, right? Anytime you have an acid derivative, be it acid chloride, be it an ester, be it an amide, okay? Right? All these functional groups, all of them, okay? When you add acid in the presence of water, you are going to get carboxylic acid, okay? You are going to get carboxylic acid. In fact, just water alone will work to make a carboxylic acid, but adding H plus is just like, is a catalyst, all right? You're a small amount. So in the first step, you're essentially going to make a carboxylic acid. Remember that, okay? So let's make sure we have the right number of carbons. So 1, 2, 3, 4, 5, 6, 7. You have a 7 carbon carboxylic acid, all right? And what you're going to get is the carboxylic acid. So you break that bond. You'll break that bond, okay? And remember, when you have an ester or an amide, whatever it is, right? You're going to get, let's make this R prime. When you hydrolyze this in the presence of an acid, okay, acid catalyzed hydrolysis is what it's called. You get a carboxylic acid and the corresponding alcohol. And also mechanistically, we know that if you have oxygen, like let's say a special oxygen, a normal oxygen, right? The labeled oxygen, okay? The labeled oxygen is seen in the alcohol side, and the water oxygen is seen with the carboxylic acid, okay? So why I'm saying this, now if you look at this cannot be the right structure because you have 2 aldehydes. Carboxylic acid alcohol, yes, 2 alcohols. That's also not the right structure, all right? So 2 is here, okay? 2 is there, all right? So let me, okay, I don't know what to erase that. Okay, so now let us look at the next reaction. So you have a carboxylic acid alcohol. When you use lithium aluminum hydride, what is going to happen is you will now not do anything to the alcohol. Lithium aluminum hydride is not going to do anything to the alcohol because that's a best lithium aluminum hydride can do. Sorry. So it will reduce the carboxylic acid now to an alcohol. So now what happens is you will convert your molecule to a diol, right? So which is going to be 3. So that is going to be 3 because lithium aluminum hydride will do that, okay? Next, what you're doing is using PCC. PCC, as we know, converts your alcohol to an aldehyde without making it into a carboxylic acid. So now here we have 1, okay? All right. Now, what is LDA? What is LDA? Lithium diisopropylamine, okay? Lithium diisopropylamine. So what is that? It's if you have isopropyl, right? This is isopropylamine. And just like you have lithium hydride or like sodium hydride, right? Positive charge, negative charge. You can also use the metal, lithium metal, right? To deprotonate the nitrogen and convert it into a lone pair. Okay. Now, amine itself is a strong base. If you use something like an amine with a negative charge, which has 2 lone pairs, this is an extremely strong base. And what it will do is it will convert your aldehyde into the corresponding anion on one of the carbons there. Okay, hopefully you guys understand what I'm talking about. This is what the enolate chemistry is, okay? The alpha carbon chemistry. So when you have a very strong base, the strong base is not going to act as a nucleophile. It will not add to this carbon center as a nucleophile. Instead, the strong base is going to deprotonate, forming the enolate, and that enolate is going to now act as a nucleophile. So LDA is a strong base, not a nucleophile. Whereas the anion you generate is a pretty good nucleophile, a strong nucleophile as a matter of fact, right? And therefore that happens. Now what will happen is 1, 2, 3, 4, 5, 6. You have a 6-carbon cyclic structure that you'll form. So you'll form that structure as you can see here, right? So that is the carbon. Let's say this is carbon 6, all right? This is carbon 6. And that is going to be, sorry, my bad. That's not carbon 6. Give me a second. Okay, this is carbon 6, right? This is carbon 6, okay, which has the anion, and that is carbon 1, okay? So you make that, and once you, so it's going to be an anion because like you have a negative species, and once you treat that with acid, the anion goes away and you get your alcohol, all right, excuse me. So now we get this structure. And finally, so this is 4, okay, this is 4. And now you treat this with PCC, you're not going to do anything to your alcohol, but you're going to oxidize your alcohol, sorry, your aldehyde, right? You're oxidizing your alcohol to a ketone. So that's what happens. So the order is 2314, which is 2314. That's the right answer. Okay. So hopefully that makes sense. Sorry for a couple of fumbles. Since I'm teaching without seeing any students, I tend to kind of lose track of things because it gets a little monotonous. Okay. So any questions about any of this? Okay, so there are a lot more problems I wanted to discuss. Maybe I'll discuss that if I have some time after this. But what I want to do is go to statement problems, but we'll take a quick break and come back at about 8:40. I'll go 5 minutes after 9:30 to make up for the missed time, and we will meet at 8:40. All right. Okay, thank you.